We have been talking about the Grover search algorithm, right? And again, whenever you see a quantum algorithm, the first thing is to ask yourself, what is that for? What problem it is trying to solve? And what is the scale of the problem? Basically, it tries to search an unstructured database. Means that the data set are randomly placed. They are not sorted or arranged in a certain way. Or in other words, means that there's no information, additional information about how they are arranged, and as a result, you cannot use that extra information to help you to search for something, right? So sometimes you need to think about it from information theory, right? Now, our goal is that, okay, I want to search for something, and let's say the index is that when it is A, like for example, the student ID, right? If I find my student ID, then I find my record, then I'm done, right? So this must be a function, right? Everything when you put into computer, it becomes a mathematical function. So basically this problem becomes saying that, can I find out which entry has this f of x equal to a equal to 1, right? So when it is a is equal to 1, so I did not say it clearly. I find an entry to find which one has f of x equal to 1, right? So when it is the one I want to search, it will return 1. If it is those that I want to search, like your student ID, I'm trying to search for my student ID, my record, right? So when I see your student ID, they will just say 0, okay? Now on average, as we said last time, if I have capital N entry, right? This is capital N, maybe let's say 1024. On average, I need to search for N divided by 2 times, right? Because it's randomly placed. So if I'm very lucky, the first one I pick up is already what I want. If I'm very unlucky, I need to pick it up until the last entry. So on average, it takes N divided by 2. And in this class, we try to say that if you use quantum algorithm, you will be able to find it in the order of square root N. Last time we talked about the complexity of algorithm, right? When we say square root N, it means the time you use to complete this computation grows up as a square root of the number of entry or the difficulties of the problem. Make sense? And classically, it is N, right? Because this is N divided by 2. Let me remind you, you can call it N divided by 2, or it's not wrong to say that this is N if we are not care about this additional factor. Because 500,000 is same for me as 1 million. It's just not difficult, right? But square root 1 million, which is 1,000, becomes much better than 500,000. Okay, any questions? So we try to just use it as an exercise to say, for example, I have 5 qubits, right? And the A can be 10010. This might be my student ID, something that my ID that I want to search. And we will be able to come up with a quantum oracle to fulfill the requirement that f of A is 1, right? When f of x is 1 when x equal to a, otherwise it is 0. So I won't repeat it one more time, but this is a very good exercise to understand the meaning of quantum oracle. It is useless in some sense because you don't construct in this way. This is just for your simulation. But if you can understand all this, what's going on, even why it is useless in some sense, then you actually understand quite well, right? So let's look at the Grover's algorithm. So how do we implement this algorithm? So the first thing is that we need, for any problem, just like classical problem, you need to represent your problem in mathematics. And here we represent the problem by saying, how do we encode my student ID, for example? In classical, you will just say, okay, it is just save my student ID as binary. But here what it does is that, okay, for each entry that I'm going to search, I encode it as the basis state. And that's what we call the basis encoding. right? You need to find a way to store the information. There are many ways to encode the problem. Some will encode it as the prefactor. For example, alpha 0 plus beta 1. You can encode the information into the phase of alpha or into the magnitude of alpha. Okay? But in this case, we encode it as the basis state. So as a result, if you remember, like what we showed you earlier, right? For example, when we say in the previous, if we use n qubits with n equal to 5, then I have this capital N equal to 2 to the power n equals to 2 to the power 5 equal to 32. It means I can encode 32 entries, 32 items that I want to search. Does that make sense to you? I need to encode it, right? So then I use the basis state for encoding. And basically it's saying that if I find this basis states, then based on the basis state, then I know the answer. Okay, this is encoding. Maybe you will understand a little bit better later, but make sure that you can come back to see to just recheck that we encode the information, what we want to search into the basis state. So for example, if I have 1024 entries, how many qubits do I need in order to encode it? Or in other words, 1024 entries means how many individual item I'm searching? 1024, right? So I need to encode it into basis. How many basis state do we need? 124 basis state, right? Which go from 0, 0, 0, or 10, 0, I mean, not 10, 10, 0 all the way to 10, 1. So it's 10 qubits. Make sense? Yeah. I can also say here we say number of qubit and basically equal to log base 2 capital N, right? Where N is the number of entries. So there are many discussions about encoding. We won't go into the detail in this class, but you will see that that's pretty cool. Because if I have 1 billion entries, I only need log 2 to the power, log 2n, right? Which is how many? 30 qubits. 30 qubits can encode 10 billion data. Now you start seeing that looks pretty good. Just 30 electrons. If I do it well, I can do the Grover search for 1 billion data. Think about that, right? And the whole world only has maybe less than 100 billion people. So maybe I just add another 3 qubits. I can, in principle, store the ID for everyone in this world just with 33 electrons. Of course, a lot of overhead is not that easy, but do you see the power, right? Okay, so that's first thing. In this algorithm, we also have 3 important vectors. We are going to study them one by one, but let's understand what they are. The first vector, of course, is the A, right? For example, earlier, A equals to 1. In the last line, right, we have A equal to what? 1, 0, 0, 1, 0. This is the one I want to search. So, of course, this is an important vector, right? Because that is what I want to search. But then after that, we also introduce another vector called A perpendicular. Can you guess what it means? I have A perpendicular. What does it mean for A perpendicular?
Bracket equal to 0.
Bracket equals 0, right, very good. Inner product equals 0, right? Or if it's in 2-dimensional space, they are perpendicular to each other. That's why inner product equal to 0. Okay, so how do we construct this? This means A, inner product A perpendicular equals to 0. So it turns out that A perpendicular can be expressed as, let me just show you and you will agree. 1 over square root 2 to the power n minus 1 square root 0 plus 1 plus 2 plus 3 plus a minus 1 plus a plus 1 plus all the way to 2 to the power n minus 1. Do you understand what you mean? Now, first of all, how many basis vector do we have in this problem? We go back to here, right? How many basis vector do we have?
N.
Capital N, right? Because we have n entries, right? So it runs from 0 to capital N. But capital N again equals to 2 to the power n. From 0 to capital N minus 1, right? And capital N equals 2 to the power n. For example, again, I have 5 qubits. If I have 5 qubits, then the value of the basis run from 0, 0, 0 all the way to, maybe I just write here, right? For example, if n equal to 5, then capital N equal 2 to the power 5 equal to 32. Right? So the basis state go from 0 to 1 to 2 all the way to 31. Make sense? But now I write it in decimal, right? You need to convert into 5-bit binary. Okay? And one of them is 10010. Now you look at this. Is this a superposition of all basis states? No. Why? Not including A. Very good, right? It does not include A. So I can rewrite it as 1 over square root 2 to the power n minus 1 summation x equal to 0, but x it doesn't let me write. But x not equal to A all the way to 2 to the power n minus 1, and then x. This looks very similar to what we learned in Hadamard gate. Remember, when I apply Hadamard gate to 0 state for n qubit, I get summation of everything. 0 to the power n minus 1. But this one is exactly the same, except I don't have A. Okay? Then based on this, would this be perpendicular to A? So, of course, because it doesn't have A component, what is inner product? Inner product is that to measure how much overlap you have, right? Now you have all the orthogonal bases, but you don't have A. Of course, you are not going to overlap with A to any extent, right? So I can also show you, right? You can see that A, inner product A perpendicular equals to A, inner product with 1 over square root 2n minus 1, summation x equal to 0, x not equal to A to 2 to the power n minus 1, and then x, right? Which is equals to 1 over square root 2n minus 1. I just take everything out, x equal to 0, x not equal to A to the power 2 to n minus 1, A inner product x. What is A inner product x? Yeah, it's a scalar, right? They are orthonormal basis, right? So it's always 0 unless x equal to A. But x is not equal to A. So this one must be 0. And as a result, the whole thing is 0. So this shows that indeed this is a vector that is perpendicular to A. Yeah.
But how do we ensure that the basis are the autonomous normal? Because we just take it from the set of the n number.
Here we already ensure it's orthonormal because we just use the basis state, normal basis state, for example, for n qubit, right? They have 0, 1, then you do tensor product. So all the basis states are orthonormal.
So the mapping from the number.
Yeah. From the beginning, right? We already choose, for example, 5 qubit, let's say spin up and spin down. Then you already have 0 and 1, which represent up and down, right? So they form a larger space, which is 5 qubit space, 2 to the power 5 space. And their basis vector are just the tensor product of the basis vector, right? So it will be 0, 0, 0, 0, 0, all to 1, 1, 1, 1, 1, 1, 1, 1, 1, right? And all these are orthonormal already. Yeah, good question. So that's why we say A and X are orthonormal. So you only get 1 if X equal to A. But since the way we construct it, we already don't have an A, right? So this one must be 0. But I do want to ask one thing. In quantum computing, every vector that is important, right, must be normalized. Is this one normalized? Why?
Because it's missing factor A.
He said because it's missing vector A, so it's not more normalized. But however, how many entries do we have here? Did I say something wrong here? Is it 2 to the n minus 2? So if I have A, how many entries do I have? 2 to the n minus 1, right? Because you miss 0. We can't find 0. So very good. He looked at this and no missing 1, so it's 2 to the n minus 2. But because we can't find 0, so it's 2 to the power n minus 1, right? What is their coefficient? 1 over square root 2 to the n minus 1. Usually, if you remember, Hadamard is 1 over square root 2 to the power 1, 2 to the power n, right? But anyway, it means I have 2 to the power n minus 1 entry, and each of them has this magnitude. If you take the square and multiply by 2 to the n minus 1, this is 1. So this is normalized. Here, duplicate entry? Oh, so he's asking what if we have 2 entries that have the same value. So there's a way to treat it. So here I again forgot to say that we only assume only 1 entry that can fit it. Yeah. But yes, people have come up with algorithm or lower bound to say, okay, what if they duplicate or what if something happened? Yeah. So we are looking at the easiest case. So good question also. Okay, so I hope I spent so much time you remember 2 important vectors. A, of course, right? You are searching for it. Come on, right? And A perpendicular, which is a linear combination of the rest of the vector. Now, because A and A perpendicular are just 2 vectors, and I know that they are orthogonal to each other, even this is a very high dimensional space, I still can draw it on a 2D plane, right? Because they are orthogonal to each other. Right? So this drawing is not a simplification. I just draw it in a plane that has A perpendicular to A perpendicular. Okay? The third vector is also important, which is phi. And this is easy. It's just the superposition of all the basis vector. Phi equals to 1 over square root 2 to the power n summation, let me call it x, equal to 0, 2 to the power n minus 1, x, which is 1 over 2 to the power n divided by 2. I just repeat 0 plus 1 plus 2 plus all the way to 2 to the power n minus 1. If you compare this with the A perpendicular, what's the difference between this vector and A perpendicular? Say again. It has an A, and that's it. So this is a superposition of all basis vector, the 32 vector, if it's 5 qubit, right? It's just an equal superposition of all vector. Everyone has a contribution. So that's why we normalize it by 1 over square root 2 to the power n, because we have 2 to the power n entries, right? Here we're missing A, we normalize to 2 to the power n minus 1, because we have 2 to the power n minus 1 entries of just another vector. Okay, but this one is very important in the sense that you see that it is a linear combination. I can call it, let's say, maybe you can find it yourself, but let me call it M. You can find out M and N later. Do you see what I mean? It's just a linear combination of A and A perpendicular, right? Of course, you need to find what is M and N when you plug in, so you get this one. But the main point is that it's just a simple two-dimensional linear combination between A and A perpendicular. And because of this, I can draw phi on the same 2D plane as this alpha and alpha perpendicular, because they're just a linear combination of them, and they're all real numbers. Make sense? Yeah. So remember, we have 3 important vectors, A perpendicular, and phi, which is just a linear superposition of everything. That's it. Then we need 2 operations, okay? V and W. So what is V? V is that if you have a vector, any vector, here we just show phi, it's going to reflect it about A perpendicular. Okay, so it was with an angle phi, theta, in the upper plane of A perpendicular, right? If I apply V to phi, then it becomes this. You just flip a mirror image about A perpendicular. Okay, so this is one vector. Now one operator. Another operator is W. And what it does is to flip any vector about phi. Okay, not about A perpendicular, but about phi. Again, just find the mirror image of this vector about phi, so it's equivalent to rotating it by 2 theta. Why we do that, we discuss later, right? But just let you know that we have V and W. One is flipping about A perpendicular, another is flipping about phi. And then you will keep applying it to bring this vector closer and closer and closer to A. And if you reach A, then it means you find the answer, because the answer is A. Okay? And it turns out that we are going to prove it. It only needs square root n time to do this operation. Okay? Then you always also need to ask yourself, how about the function? Yeah, you embedded A, but where we put the function? Because you try to solve a problem means you need to take the function into account, right? The function is f of A equal to 1 and f of A x not equal to A equals to 0. We embed this function in V. So the way it flips about A perpendicular will depend on the function. And because of that, it will be able to help you to go 5A. And this is very normal. You cannot embed it in W because you're flipping about phi. Phi has nothing to do with A, right? Phi is a superposition of everything, right? But if you embed in V, then you will let it flip about A perpendicular, and eventually you will find A. Okay, so maybe a little bit confusing now, but that is the idea of the algorithm. How do we know what? How do we know phi has reached A? Yeah, so you apply based on theory, how many flips do you need? We are going to show you, which is about square root n. And then you will do a measurement. Because you cannot get to A exactly, right? It may have a little bit angle, right? So it becomes A plus something else. But something else is very small. When you do a measurement, there's a very high probability that you will get A because it will collapse to A or A perpendicular. Make sense? Right? You do measurement. That, which one? Let's say something like this, right? It's not 5, but eventually you have this wave function, right? When you do measurement, you collapse to A or collapse to A perpendicular. But when you're very close to A, particularly when the size is large, you will be able to be very close to A. You do a measurement. You have a very low probability to get A minus, right? Mostly you will get A. If you're unlucky, you get A minus, what do? You look at it. That's not what I want to look for. Do it again. But you have very high probability the second time you will get A. Then you get what you want. So that is another thing you will see later in Shor's algorithm. When you do this quantum algorithm, it does not guarantee to give you the answer. But the good thing is that you have a high chance to get the answer. And if you don't get it, you just run the algorithm again, because they have an exponential speed up in those algorithms. Here only square root, right? But because you have high chance, it's a very low chance you will get the wrong answer in the second time, right? Because let's say 0.1% chance. You want to get wrong answer in 2 times, it's like 0.000001, right? 10 to the power minus 8, right? That's almost impossible, right? And if you are so lucky, then you just go to buy a lottery. Probably it's better than studying quantum algorithm, right? So yeah, so the nature is very interesting. Yeah, so that's a good question. Okay. So let's start doing some math, right? So let's try to understand how we can implement V, right? So that is what we are going to do. We are going to define an operator V applied to a state Vn. Again, any operator is a gate, and we define the gates by how it transforms the basis state. When I say x, means x equal to 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, right? It's defined as this: -1 to the power f of x, xn. This is a quantum oracle. What type of quantum oracle is this? We have learned 2 types: exclusive OR and phase. Phase, right? It doesn't look like exclusive OR, right? Yeah, phase. You see that it embeds the function f of a into v. Okay? So what does it mean? It says that if x equal to a, then v of xn is going to be equal to -1 f of a xn equals to, what is f of a? 1, right? That is what we are searching, right? So this is equal to -xn. Is that okay? But if x not equal to a, then v of xn is equal to -1 to the f of x not equal to a. What is f of x not equal to a? 0. So this is just xn. Right? And that's why this is this is called phase oracle, because it changed the phase. Because this is f of a equals to 1, f of x not equal to a equals to 0, right? So that's it. That is the oracle we are going to use, right? How to implement it is another thing, but no, that is phase oracle. We assume we can implement it. Okay, but does it do the work? I say, what does it do for V? It flips the any vector about a perpendicular. Okay, so let's show that. Let's check if it flips any state beta about A perpendicular. Okay? Now, but we will check for we need to check for beta on the plane, on the 2D plane, right? Because that is what we need in this exercise. So if it's on the 2D plane, beta can be written as beta 0 A plus beta 1 A perpendicular. Are you okay with this? It's just like our regular geometry, 2D plane. Any vector equal to x hat, A times x hat plus B times y hat. And that's why I'm saying beta A, beta 0 A plus beta 1 perpendicular. Okay? So now if I apply V to beta, it means I apply V to each of these components, right? Because it's linear. Any questions? I apply V into the whole beta, then it's equal to apply to each individual component, correct? But what does this oracle do? It's just equal to beta 0, negative 1 to the power f of A, right? Because we already said that when you apply to a basis state, it's negative 1 to the power f of x, and then just keep whatever you apply to, right? And how about the second one? Same, but this time is f of A perpendicular. This one I skip a little bit. If I say A perpendicular, you might get a little bit confused because A perpendicular is not a basis state. Right, do you understand what I mean? So maybe let me rewrite it. Maybe it's better I rewrite it in this way. So sorry for that. Let me just write one more time so that you will understand better. So this one, I keep the first term. VA is the basis state. The second term is going to V, but what's this A perpendicular? If you go back to here, it is 1 over square root n minus 2, and then sum over all the basis state, right? So it is 1 over square root 2 to the power n, 2 to the power n minus 1, sum over x equal to 0, x not equal to A, 2 to the power n minus 1, and then x. Are you okay with this? This is A perpendicular. This is all basis state except when x equal to A, right? Okay? So I can apply this into it, right? So then the first term, of course, is beta negative 1 to the power f of A. This is okay. We apply to A is equal to negative 1 to the power f of AA. Because f of x equal to A. And I do the same thing for the other term. I apply V to x is just equals to beta 1 over square root 2 to the power n minus 1 summation x equal to 0, x not equal to A, 2 to the power n minus 1. I have negative 1 to the power f of x not equal to 0, not equal to A, x. But what is this value? Let me just save the writing. What is this one? Negative 1 to the power f of A minus 1. How about this term? Negative 1 to the power f x not equal to A. 1, because they are all 0. I don't have A there, right? Then with this, then this is still equal to A perpendicular. So I have this equal to negative beta 0A plus beta 1 A perpendicular. Is this okay? Any questions? I know my writing is really ugly. Any question? Just ask. It's confusing. Yeah. Which? You mean this one? Because the left term is only A. Left term is just A, the basis vector that we are trying to search for. So let's say in this case, the A is 1, 0, 0, 1, 0. This is the basis vector. But for right term here, this one is A perpendicular. A perpendicular is a linear combination of many basis vectors except A, right? So that's why I change A perpendicular to this whole term. This whole term is A perpendicular. Yeah, good question. And then I can multiply it one by one. Okay, good, very good. Any other questions? But if you look at this compared to the original beta was beta 0 alpha plus beta 1 A perpendicular. Now it becomes negative beta 0 alpha plus beta 1 perpendicular. What does it mean? I don't have space, but I can draw it, right? Just look at this. What? So this is A perpendicular. This is A. If I have a vector, let's say this is beta. If this is beta 1, this is beta 0, then this is beta, right? Because it's beta 0 times A plus beta 1 times A perpendicular, right? That equals to beta, right? I decompose it into X and Y. After flipping, what does it look like? It says that, well, you still have beta 1 as the beta coefficient of A perpendicular, but now you get negative beta 0, right? So it means I do flip it about A perpendicular, right? So this is just a proof saying that, okay, if you have a phase quantum oracle in this form, you achieve the goal of flipping any vector about A perpendicular on this plane. Any questions? Yeah. What do you mean by positive and negative? Which, what? Oh, yeah. So his question is why you flip the other side, right? We will see that later. We don't only use V, later we use W. So W will bring it anti-clockwise back. So you need V, W, and W is going to rotate more than V. So your net effect is keep rotating counterclockwise to A. Yeah, so this is only one step. Yeah, good question. But the most important thing is beta is any vector. So you don't need to worry about later you rotated the vector already because it's going to flip again about A perpendicular. Okay. How do we implement this quantum oracle, right? So based on what we saw, we try to flip it. So it means that we just say that beta equals to beta 0A plus beta 1A perpendicular, right? That means that, and then if I apply V to it, I will get beta 0A negative beta 0, negative beta 0a plus beta 1a perpendicular. Right? So I can rewrite this as beta 0a plus beta 1a perpendicular minus 2 a. 2 beta 0a, sorry. So what I'm trying to do is just that I know the final form. Of course, when people derive it, they also have a path, right? They have the insight. But what I'm trying to do is just say this is negative x, negative, not really, right? Negative O. Then it become O minus 2O. That's it, right? Because beta 0a minus 2 beta 0a give me negative beta 0a, right? So I can basically say that this is just, we can set V equals to I minus 2A. We need to find a quantum oracle in this form, right? We can check. Let's see if this is, let's check. V applied to beta equals to V applies to beta 0a plus beta 1a perpendicular. Correct? And then we say V equal to I minus 2a, the whole thing times beta 0a plus beta 1a perpendicular. So I'm just not going to go to detail, but I want to remind you, right? What is A inner product A? Again, 1. What is A inner product A perpendicular? 0. So you see that I have a few terms here. First is just I times everything. Then I get 0, beta 0a plus beta 1a perpendicular, right? This is the first term. I times the whole thing. Right? Now, I still have these two A outer product multiply A, right? And then minus 2 beta 1 A outer product A perpendicular. I know it's confusing, but look at this. This term times this term is negative 2 beta, and then A outer product A inner product, times A, right? So this one give me 1. And for the second term, negative A outer product times beta 1, there I have got negative 2 beta, and then A outer product times A perpendicular. I'm missing a line. This one equal to 1, but this one equals to 0. So as a result, this equal to beta 0a, or just negative beta 0a plus beta 1a perpendicular. Okay, so this is a way to implement the quantum oracle, right? It achieves the purpose. And it makes sense because now it contains A in the quantum oracle, right? Because we're trying to searching for A, there's a way you need to have A. But exactly how to implement, then you need to decompose it into more primitive gates, and there's something we don't discuss here. Any questions? Yeah.
I should say that in the second row, right, you have the term minus 2b factor A.
Yeah.
Then so I don't see it in the expansion in the last row.
Yeah. Yeah. So good question, right? So first, I times this whole thing, you get this. Is that okay? I times this whole thing. I times beta 0A plus beta, you get this, right? And then you need to do negative 2 outer product A times beta 0A, right?
Yeah.
This is negative 2 beta 0 outer product A times A, right? But due to associative rule, this can be grouped first, right? A inner product A. So this one becomes 1. Then you get negative 2 beta A, right? This term. But how about the second term? This whole thing times this one. You do the same thing, negative 2 beta 1, and then A outer product A perpendicular. But you have inner product of A and A perpendicular, which give you 0. So this term is gone. Good question. Any other questions? Again, if you ask question, you're helping others, right? Because you're sure not the only one who got confused by me. And the whole idea here is that, of course, it's difficult to come up with this idea. You need to be very, savvy in quantum computing, right? And I do this just because I got the answer from textbook already, from people's invention, right? But here it's just we practice the skill again. We show that how we can show that this V constructed by this implement this function of phase oracle, or that you reflect it about A perpendicular. Okay, so if you forget everything, fine. That the most important thing is you should agree now. V flip any date vector about A perpendicular. Okay, it works by constructing it this way. Then we need to look at another operator, the W operator. And as we said, it will flip any vector about phi. Okay, so, and again, someone gave us already, it is given that we can construct W equal to 2 outer product phi minus 1. Again, what is phi? Is the linear superposition of every basis vector. Is that okay? The definition. Okay, this is given, right? So we are going to check, right? Let's check if it flips vector gamma. It can be beta, but just call it gamma, right? On the plane. Again, we only care those on the plane because we never rotate it outside of the plane. About phi. I use the same method, gamma on the plane. It can be written as gamma 0 phi plus gamma phi perpendicular. We did not define what is phi perpendicular. But of course, I can always find a vector on this plane that is perpendicular to phi, such that phi inner product with phi perpendicular equals to 0, right? And this is the vector that we've shown here. So, okay. We said phi is just a linear superposition, equal superposition of every basis vector. And earlier I claimed that it must be on this plane. And if I have phi, of course I just draw a vector perpendicular to it, and then that vector is phi perpendicular. There are many phi perpendicular out of the plane also, but those are not what we are interested in, right? There are many vector perpendicular to phi, but we just look at this particular phi perpendicular that is on this 2D plane. And of course, because of that, this form another coordinate. So if beta can be expressed by a linear combination of A and A perpendicular, it can also be expressed by a linear combination of phi and phi perpendicular. Right? It's just like in 2D coordinate. Y becomes X dash Y dash. right? So I can express it in this way. And so now I'm going to show that W indeed has the same function, has the function that we want, and we use a very similar method as what we did before for V. So W applied to gamma give us R0 W phi plus, gamma 0 W phi times gamma 1 W phi perpendicular. And I forgot to say, of course, gamma 0 squared plus gamma 1 squared equals to what? 1, right? Every vector needs to be normalized. So let's just plug in gamma 0, and then I say W is 2 phi outer product phi minus 1 times phi. And then gamma 1 W, I need to plug in W, 2 phi outer product phi minus 1 times phi perpendicular. Are you okay? This step is messy but should be straightforward. Phi times W times phi, right? I just plug in W because it's given that W equals to 2 outer product phi outer product minus 1. Okay? And you just continue, but it is very clear, right? The first one, you just do distribution law, gamma 2 phi minus phi. Second one, gamma 1 2 phi perpendicular minus phi perpendicular. Maybe very long, but you just do it step by step because I just multiply phi to here, so it's 2 pi phi inner product phi. And multiply by I, then it's just itself. Similarly, phi perpendicular goes in, then I have 2 phi inner product phi perpendicular, goes to I, becomes negative phi perpendicular. Right? And again, what do you see? What do we know? What is the inner product of phi? Must be 1, right? It's normalized. We just said that earlier. And how about phi inner product phi perpendicular? By definition, right? It is 0. So with this, then it's simplified to 2 gamma 0 phi, right? Minus gamma 0, is that right? Okay, so I don't need to do, okay, I maybe do one more step. Phi plus, not plus, minus 2, no 2. What is that? Minus what? Gamma 1 phi perpendicular. Very good. Yeah, a little confusing, right? So this one is 1. So it becomes 2 phi minus phi, which is actually phi. I'm just too slow. But it's just 2 gamma 0 phi minus gamma phi. 2 gamma 0 phi minus gamma phi. And then this 1 0 is gone. So I only have negative gamma 1 phi perpendicular, right? So the whole thing is just equals to gamma 0 phi minus gamma 1 phi perpendicular. Correct? So what does it mean then? Then let's draw a diagram again. So this time we are going to have phi. I do it a little bit tilted. This is phi. This is phi perpendicular. So originally I have a vector, let's say here. This vector is called gamma, and it has this component. It has gamma 0 phi and gamma 1 phi perpendicular, right? It's negative, but doesn't matter, right? It can be negative. And then what happened after rotation? I becomes this vector when I apply W to gamma. It still have gamma 0. Did I say something wrong? Yeah. Correct? But it becomes negative gamma 1. Right? It doesn't matter. Do not keep thinking that, oh, this is positive, but gamma 1 can be negative, right? Then this becomes positive. The main point is that I flip about phi by applying W. Okay? Any questions? Oh, it could be faster. Okay, so how do we implement W then? We just say that W equals to 2 phi outer product phi minus I. And you probably at this stage, you were able to memorize something, right? It's outer product. It's very similar to this one. I minus 2 outer product, right? And this one will flip about A perpendicular because you have negative 2 outer product A. And this one will flip about phi because it's positive 2 outer product. The math will just make it flip about that, right? Because the flipping is that you keep one component the same. The other component, you negate it. Okay? So this is W. So if we want to implement it as a quantum gate, then let's see. Okay. First of all, how do you get phi? Do you remember? Phi is just the equal linear superposition of all basis vector. How do you implement it? Use which gate? Hadamard gate. Correct. You just apply an n-qubit Hadamard gate to the basis state 0. So this is easy to implement the phi, right? We derived that earlier. Okay. Now then we also need to say that then what is phi outer product phi? Of course, then it's equal to 0 Hadamard gate Hermitian conjugate Hadamard gate 0. I hope you understand. Oh, I say it wrong, right? Am I right? I'm right. No, what I'm doing. This is wrong. Wrong direction. Yeah, sorry, I'm completely wrong, right? What? Did I do something wrong? Do you see that? I'm sorry. What is the cat? Cat is this, right? Correct. And what is the bra version of it? Is this, right? Do you remember this? Yeah? Because just recall, for any function, if you have, let's say, A applied to a function psi, its bra version is psi A dagger. Remember, this is the bra version, bra space. No, this is the cat space. I'm sorry, I keep saying the wrong thing. This is the cat space. This is the bra space. Right? So what I'm doing is that, okay, this is the cat because this is cat psi, and I apply Hadamard gate to 0, and this is the bra, becomes bra, and I have this one, right? Hermitian conjugate. But what is the Hermitian conjugate of Hadamard gate? It's just itself. Very good. Okay. So that's why I will get Hn 0n 0n Hn. Okay, so that is the first thing. Now then, I also have a 1 identity. And I claim that identity equal to this. Of course, when I put I, it means it is the n-dimensional identity gate. I claim that this equals to this. Are you okay with this? Identity gate equal to Hadamard gate times identity gate times Hadamard gate. Is this correct? Why is correct? Can you prove to me very fast? Huh? That's not enough. Unitary and Hermitian. No. I'm talking about this equation. Nothing to do with 0, 0. I equal to Hadamard gate times I times Hadamard gate. Good. I have no, follow him. I have Hadamard give Hadamard gate, so it become HHI, and then why HHI equal to I? Very good. The Hadamard gate is its own inverse, right? So H times H equal to 1. So I jumped the step, right? Because H equal to I. Then, so HI equal to I. H equal to I. And that is what I have on the left. I equal to HIH. Right? So you can just do whatever you want. It is its own inverse. Remember this. Right? Okay? So because of this, then now I can rewrite this W equals to H2H, this 0, 0, H, this minus H, I, H, H, right? What I'm doing is just substitute this I to here and this substitute this to here, right? So as a result, I will get H outside 2, 0, 0 minus I, and then H outside. So basically, I only need to implement these gates and then put Hadamard gates at the beginning and at the end. Then I will get the W. Now, how to decompose that is another art, right? If it is 1 qubit, this is just the Z gate. The whole thing is just Z gate. And if it is many qubit, you can use control Z gates to come up with a complicated circuit, right? So here just to show you, okay, you have the idea of rotating a vector or flipping a vector about phi. Good, and you come up with this equation. But then you need to implement in quantum gate. And there are many ways. Some people come up with this expression. And then from here, they have some other way to decompose this into control Z gate or whatever. And these are just Hadamard gate. So eventually, your quantum circuit is a bunch of Hadamard gate, and then some control Z gate and other circuit, and then Hadamard gate. And this is the one that will do the work for W, that flip your vector about about phi. Okay, but we'll not go into detail. Make sense? So this one may be implemented by X and control Z gates, etc. Okay, just a note. Okay, that's good. So remember, we have 3 vectors. Let me come back. We have A, what we are searching for, A perpendicular to it, phi, which is a superposition. We also have 2 methods. We are able to flip any vector about A perpendicular, which is V, which contains the information of the function. We also can flip any vector about phi, which is W. And based on this, now we want to go to deeper to find what is the angle between A and phi. This will help us because if I start with phi, flip it, then it will come here. Flip it again, you go to the top. Flip again, you go to the bottom. Flip again, go to the top. Flip again, go to the bottom. Eventually, I go to A. So my goal is, well, how small is this theta? Okay, So let's take a look. What is theta? Theta is related to the inner product of A and phi. So A, inner product phi, this is a 2D plane, right? Because it's 2D. So it's basically the magnitude of A, magnitude of phi, times what? Do you remember? What is the inner product? Cosine theta. Very good. And these are what? What is the magnitude of A and phi? They are all one. Good. Right? But this also equals to what? A, inner product of 1 over square root 2n, summation x equal to 0, 2 to the power n minus 1 x. Because this is the definition of phi. Are you okay with this? A inner product with phi is just A inner product with the superposition of x from 0 to 2 to the power n minus 1. When you have A goes in, what do you get? AX. A inner product of x equal to what? What is A inner product with x? X are what? Are the basis state, right? I know coefficient square. I need you to give me the answer. What is the answer? Okay, good. Equal to 0 if what? When is equal to 0?
When A different from A.
When A not equal to x. Equal to 1 when what? A equal to x. So I decided not to write in this way. We need to be, we are very advanced now. Equals to delta AX, right? Whether A equal to Kronecker delta, right? So this one will give me what? Only one term will be 1. Every term will be 0. So this is going to be 1 over 2 to the power n over 2. That's it. Because I have 2 to the power n terms, only one term will give me 1. And that give me 1 over 2 to the power n2, right? But, so it means, so I say something wrong. Very wrong from here. No one catch it. No one caught it. This is not cosine theta. Because I'm asking the inner product, the angle between A and phi, not A and A perpendicular. Okay? So what is that? It's cosine what? Their angle is pi over 2 minus theta. Right? Because this is the angle between phi and A. Okay? So this math tells me that cosine pi over 2 minus theta equals to 1 over 2n over 2. But what is cosine pi minus theta? Thank you. Sine theta equal to 1 over 2 to the power n over 2. But when n is large, when n is very large, let's say 100 qubit, you have 2 to the power 50. What is 1 over 2 to the power 50? Super small, right? Theta must be small. And we use quantum computer only for large problem, right? I don't care if you're solving a 2 qubit problem. It's meaningless for me. So in that case, sine theta is approximately equal to theta, right? You just look at the table. It's true. 0.001. Sine 0.001 give you about 0.001. So it means that at this time, theta equals to 1 over square root n. Right? Because n equals to 2 to the power n. Right? This n may be 1 trillion, and which is just have how many qubits? 40 qubits, 1 trillion. Yeah. About, yeah. Okay. So n is theta. So based on this, how many VW operation needs to bring phi to A? Right? So how many operations do I need to bring it to A? So I'm sorry I did not plan this well. So I'm going to here. It's going to be pi over 2 minus theta divided by theta. Right? Because the angle between phi and A is pi over 2 minus theta. And this angle is theta, right? So how many operators do I need? It's going to be, but theta, pi over 2 theta minus 1. But theta equals to what? Square root n. 1 over square root n, right? Did I do something wrong here? I'm sorry, yeah, should be 2 theta. But actually, I jumped too much. I should have not talked about how much it rotates in each VW. I go too far. So, sorry. All I want to say is that theta is very small. Sorry for this. So we stop here. I mean, for this slide. All I want to say is that when you have enough qubit, 30 qubit is enough, theta is super small, right? And theta is 1 over square root n. That is theta. Okay, and that should be 2 theta, but I jumped, and that's why I messed up. Is that okay? So then, let's take a look again what it does. I just want to remind you. So for V, we have A perpendicular here, A here. So I have a vector which is Y. And if this is alpha, this is the angle, it's going to flip about this one, right? Becomes Vy. Is this okay? That's the function of V. V flip about A perpendicular, right? So equivalently, it means it rotates Y clockwise by 2 alpha. Right? So that is the operation of V. It rotates clockwise by 2 alpha. And if Y is actually phi, if we use phi as the beginning, if Y is actually phi, then it rotates by 2 theta, because that is the angle between phi and A perpendicular. Okay, so there's nothing special, right? Just that it rotates it by 2 alpha or 2 theta. Then we come back to another W. What does W do? A is here, A perpendicular is here, and then we have phi here, right? So I may have a vector which is Y. And this time I call the angle be gamma. Gamma is between Y and phi. And what it does is to flip about phi when you apply W to Y, right? About phi, not A perpendicular. So its effect is rotate anti-clockwise by 2 gamma. Okay, so now we simplify it to, for V, you rotate it clockwise by 2 theta. And when it is phi, you rotate it anti-clockwise by 2 gamma. Theta is the angle between the vector and A perpendicular, and gamma is the vector, is the angle between the vector and A and phi. Okay. Then we will combine them, but I think you are tired already, so I will do that next class. And then we will show that it rotates by 2 theta, and that was the mistake I just made. If it's 2 theta, then you will get how many times it will rotate. Okay, so almost done with this growth algorithm.